This video will look at the Poisson distribution, the Poisson function. In statistics there are several notable distributions, and it's important in the study of statistics to go across these. For example, the Poisson, as we've got here, the binomial, and there are several others. But in particular, probably the Poisson and the binomial distributions are essential. Now, the Poisson distribution, well, it's normally associated with events that occur independently, and we have to work out the probability of an event happening. And the Poisson distribution gives us a formula to enable us to work this out. So suppose that we want to investigate the probabilities associated with cars arriving at a road junction. Now, it may sound obscure, but there are plenty of business problems and issues that can be related to this. Not to the cars arriving at the junction, but business situations where receipts into the stores, for example, deliveries into stores, or some issue in the company, providing that the instances are independent and providing that they're measurable and there is no bias or obvious bias in the situation, then we could apply the Poisson distribution. But the classic example is this one of cars arriving at a road junction. So let's say you were planning traffic in a particular area. You may be interested, what's the probability of a certain number of cars arriving at the junction at a particular moment in time? So say, for example, on average, let's say 22 cars arrive at the junction in an hour. That means in a specific hour of a working week, just so we have a standard. So let's say cars arriving at the junction between 9 a.m. and 10 a.m. Monday to Friday inclusive. Now let's say we want to calculate the probability of exactly 18 cars arriving at the junction in an hour. Now on average 22 arrive, but we want to know what's the probability of 18 cars arriving. We're going to plan the road layout in a certain way, and we've estimated we want to know what's the probability of 18 cars arriving, just as an example. Well, the easiest way to do this is to use the computer, of course, to perform the calculations. That's what computers are good at. They're good at doing calculations. But we may do it in two ways. We may carefully enter the formula that corresponds to the Poisson formula. So we may enter this, let's say enter it into Excel. Or alternatively, we could use Excel itself just to bring up the Poisson expression. And this is probably the easiest way of performing the calculation. So Excel will calculate the Poisson distribution and the probabilities for us. It's a function of Excel. So we could do it two ways. Once we could enter the formula into Excel and work out the answer, or we could get Excel to just perform the whole thing itself just by entering the data and telling Excel to process the data using the using the Poisson formula that's built in. Let's look at entering the Poisson formula. Well, if on average 22 cars arrive at the junction in an hour, and we want to calculate the probability of exactly 18 cars arriving at the junction in that particular hour. Let's say, as I said, between, let's say, 9 and 10 o'clock in the morning, weekdays, so Monday to Friday inclusive, including Mondays and Fridays. Now the Poisson distribution is this one here. This is the formula that should be used. You see that the formula, the Poisson distribution for x, which is equal to lambda. I'll just put the cursor onto the screen for a second. Lambda is this Greek letter here, lambda to the power of x, hopefully you can see that, times e is a constant in mathematics, 2.7 and so on. It's an irrational number, so we can't write it down. It just goes on forever, a bit like pi. But e is a constant in mathematics. E to the power of minus lambda all over x factorial. In other words, x times x minus 1 times x minus 2 times x minus 3 and so on until we get down to 1. So that's the Poisson distribution. Let's see how to enter it. Well, what we know from this formula is, in our question here, we've got lambda, the average rate of arrival, which is 22. We're told that in the question. 22 cars arrive on average. We know that E is 2.72, so on and so on. That's a constant, but it's an irrational number. We just simply classify it as E. And X is what we want to calculate. We want to know what is the probability of exactly 18 cars arriving at the junction in a given hour. We know that 22 on average arrive, but we want to calculate the probability of 18 arriving. Now we could do this by using what we call power functions, and Excel has these built in. So we could say, for example, x, if we say we have a power expression like power bracket 2 comma 1 close bracket, that would be 2 to the power of 1. Well, 2 to the power of 1 is just 2. So if x is equal to 2, now x cubed, well, we know if x is equal to 2, x cubed is equal to 8. And the formula in Excel for that is equal to power, just type in the word power, bracket 2 comma 3. The 3 corresponds to the cubic expression, the exponent of x, so it's x to the power of 3, which means 2 to the power of 3, which is 8. X to the power of 4 is equal to 16, which is equal to the power expression power bracket 2 comma 4 close bracket. So it means 2 to the power of 4, which is 16. So we could use these power functions in the formula. Let me just put the cursor back on the screen for a second. If we go up here, we can see there's a lot of powers here. Lambda to the power of x, e to the power of minus lambda. So we could use these power functions here to calculate those. If we write out the Poisson formula, this one here, if we write it out in terms of power functions, we'd have this expression down here. We'd have equal to power, well, here we'd have f5, 22, which is lambda. Where's our lambda? Up here. 22 to the power of x. Well, x is f7. So it's power f5 comma f7. So that gives us this one here. Now times e to the minus lambda. So it's times, here's the times, power f6. f6 is e, 2.72, etc., etc. It's a constant in mathematics, but it is an irrational number. So we just write it down to a couple of places of decimals, generally speaking. So 2.72. So f6, and it's f6 to the minus f5. f5 is 22. minus lambda. And all of that is divided by factorial, F-A-C-T, F7. So all divided by x factorial. In other words, 18 times 17 times 16 and so on. And when that's all multiplied out, we get the number 0.0635. So using the Poisson expression, which is an alternative, we get the same answer. Surprise, surprise. We should get the same answer because it's the same question. But the Poisson, using the Poisson expression in Excel, we just simply equals Poisson, and then we enter the data. We have F7. F7 here is lambda. F5. Sorry, F7 is bigger pardon is x. F5 is lambda. So we'd have F7, F5, and we have false. False is a switch. It's called a switch in when we're using these formulae. So the Poisson distribution probabilities. Well, the Poisson function calculates probabilities for Poisson distributions. Obviously, the function uses the syntax equals Poisson x mean cumulative, where x is the number of events. It's really the arithmetic mean. X is the arithmetic mean, and there's a cumulative switch, which is false. Let's talk about that switch for a second. Here it's false. Well, if it's set to true, the switch tells Excel to calculate the Poisson probability of a variable being less than or equal to x. In other words, we'd calculate the probability of one car arriving, or no cars arriving, one car arriving, two cars arriving at the junction, 3, and so on, up to 18. And it works out the cumulative of those. So what's the probability of up to including 18 cars arriving at the junction? If it's set to false, it tells Excel to calculate the Poisson probability of a variable being exactly equal to x. In other words, exactly 18, not 17, not 16. It doesn't add up anything. It's not cumulative in that sense. It's false. So we have the word false in there to tell it we want exactly 18. Now, using the Poisson expression, well, Poisson, that is the formula that we used. It indicates that there is approximately 0.64 chance of there being exactly 8 cars at the junction. Remember that the average was 22. In other words, there's a 6.4% chance of exactly 18 cars at the junction. It's a small percentage because we know that the average is 22. So 18 is significantly under 22. So we'd expect it to be less. To calculate the probability that 18 cars or fewer will arrive in an hour, we use the formula Poisson 18, 22, true, as I said earlier. The function returns the value 23.3%. This means that the probability of any number of cars from 0 to 18 arriving at the junction in a given hour is approximately 23%. The probability of exactly 18 cars is 6.4%. The probability of 0 cars, 1 car, or 2 cars, or 3 cars, and so on, 17 cars or 18 cars. If we add that up, the probability of any of those numbers up to and including 18, well, that probability is 23. And that's a brief introduction to the Poisson, how to do a particular calculation with the Poisson function. We aim to have more classes on various distributions throughout the course, and it's important that you just generally read up on the background to these type of distributions to get a feel for how they can be used in a business setting. But that's all we're going to deal with in this class, so let's leave it at that and say thank you for watching.